Hello. The goal of this course is to answer a question that humans have asked generation after generation, especially in times when light pollution did not block our wonderful view of the starry sky. That spectacle, which I highly recommend, has, besides its beauty, the great virtue of inducing deep reflections on the nature of the universe. And surely, the first one is, how high is the sky, that vault that covers our world? During the day, if it's clear, we can see above us a blue ceiling and presiding over the scene, a yellow sun. The sun is actually white, en kaifan, ja sun is astrosalius, the first astrosuyeu, and we would see it that color if we could leave our atmosphere. Since we are below it, the sun's white light must pass through it to reach us. All white light would be the sum of all the colors we can see, which are not treated in the same way as the atmosphere. The more violet and bluish colors are more sensitive to the small obstacles that stand in their way. They bounce off those obstacles in all directions and thus become more visible, tinting the sky. Blue ends up predominating because it is more present in sunlight than violet, and also our eye is more sensitive to that color. On the contrary, red and yellowish colors are not as sensitive to the obstacle of our gaseous layer. Those parts of sunlight are deflected less and reach us more directly. For this reason, we see the sun as yellow. The process is more pronounced the greater the density of gaseous obstacles for the light. The atmosphere, despite being a gas, has weight and presses against the ground. Therefore, its density is greater at ground level, and the scattering of blue is also more pronounced. Yes, the blue color of the sky starts to form right in front of your nose. It happens, therefore, that it is a weak phenomenon, and you do not notice it unless a large layer of gas accumulates in front of your view. 90% of the atmosphere is concentrated in the first 20 kilometers of height due to the pressure caused by its own weight. So most of that blue tinting process will take place in that area. From 25 kilometers upwards, there is no longer enough gas density to create this sensation, leading us to our first conclusion: the daytime sky, that blue ceiling, is about 25 kilometers high. If someone organized balloon trips to surpass that height, the passengers would start to see the black sky and the white sun as if they were astronauts. An experience not very different from what is had in the tourist spacecraft of Richard Branson or Jeff Bezos. In fact, to se posedita balloon at that height above the vertical of Madrid would have a horizon view of almost 600 kilometers, which means it could see all of Spain at the same time. Jeff Bezos' spacecraft, which rises to 100 kilometers in height, has a visible horizon at only double the distance. So you see, there isn't as much difference as one might initially imagine. We will explain how to calculate this in a later chapter. But so far, we have only talked about the daytime sky. When night falls, that sky seems to grow and be much larger. Yes, indeed. Since the sun is not shining, that blue wall created by the scattering of part of its light, which prevents us from seeing beyond, disappears. Now we have the real sky in front of us. And this is where the story of humanity's struggle throughout history to answer the question that gives this course its title takes serious shape. And to start calculating, we will first need to know the size of our planet. If any of us were asked how to represent the Earth, we would immediately say it is round, a ball. We know this because from a young age, we are taught that it is so. We live in a very particular time in which we had the privilege of being able to leave our planet and see it from the outside. But this has only been happening for half a century. Here we make a parenthesis to introduce a small nuance. It is not a perfectly spherical ball, as it is slightly flattened at the poles, and this is because the Earth rotates on its axis. The effect is the same as when you take a wet ball and spin it on an axis. You can observe how the drops tend to slide towards the equatorial zone where there is more speed. Well, even though it seems unbelievable, we can say that the Earth is somewhat soft and therefore something similar will happen to it. The matter it is made of will tend to slide towards the equatorial part, causing a slight thickening in that area like a spare tire. The result is that the Earth will have a longer circumference at the equatorial zone than when passing between the North Pole and the South Pole. The distance from the equator to the center of the Earth is about 22 kilometers longer than from the North Pole to the center. That represents only a variation of 3 parts per thousand, so it is hardly noticeable The circumference of the equator measures about 70 kilometers, more than those passing through the poles called meridians. For the meridians, the radius varies as you move from north to south, so we conclude that the meridians are not actually as round a circumference as the equator. But let's get back on track. The truly important question is the following. How did our ancestors come to this knowledge of a ball-shaped Earth? In principle, si danos tos es como si te afeite, y it doesn't seem like anyone could assert something like that without using a spacecraft. Imagine we sit one day in a place clear of obstacles and look as far away as possible. If we turn around, even if we see the irregular profile of mountains or buildings in the distance, the sensation will be as if we were on a large plate. Therefore, Sam, que se l'entendo, reflecting po, as opposed to look forward by mere observation. The first thing that would occur to us is to think that the Earth is flat, with more or less elevations of the terrain, but on a flat base on which everything rests. Above it will be the sky, blue during the day if it's clear, and black with little lights at night. It would be logical to say that it is like a dome covering this entire landscape, is something like what is depicted in this well-known illustration. Many years ago, around 500 before Christ, Hecataeus of Miletus reasoned in a way similar to what is shown in the drawing. For him, the Earth was like a disk with its center right where he was looking, which was Greece. However, the Earth had to be an island, as it was surrounded by the water of the Mediterranean Sea. Do not think that he was satisfied with just visual observation. No. In addition to that, he estimated that the diameter of that disk was about 10,000 kilometers. But other Greeks who came shortly after thought better of it. They were used to seeing the sea and realized that when a ship advances toward the horizon, there comes a moment when we lose sight of its sail. It's as if it falls beyond the horizon you can see. Interestingly, for every meter we rise above sea level, our horizon will be at a distance in kilometers obtained by multiplying 3.6 by the square root of our height expressed in meters. That is, if your eyes were 1 meter above sea level, your horizon line would be at 3.6 kilometers. If you were at 100 meters of height, the horizon line would be at 3.6 times the square root of 136 kilometers. By the way, if you remember what we talked about earlier regarding Jeff Bezos, we said that he goes up to 100 kilometers and our balloon went up to 25. That is to say, Jeff Bezos goes up 4 times higher than us. And as you can see, since what makes the difference is the square root of the height, Jeff Bezos goes up 4 times more and therefore has only double the horizon. We conclude that the Earth is not flat. Does the sea swallow the ships? They must have thought. The only solution seemed to be that the Earth curves. There was another piece of evidence, no? When the Earth is right between the Sun and the Moon, it covers the Moon, causing what is known as a lunar eclipse. At that moment, the Moon acts as a screen to project the shape of our planet. It's the same thing a louse living on our head would have to do to see what we look like. Ask that we be enlightened and see the shadow we cast on a wall. Shadows, as you see, shed a lot of light on investigations. But above all, once we sense that the Earth is a sphere, how can we measure it? That is what we will reveal in the next chapter.